So are everyone hearing my voice?
Yes.
Okay. Good morning again. Let me first thank you, Dr. Tuna, for her great presentation, and also because although she wasn't feeling very well, she managed to teach today so that the integrity of our course is remained. Just as a little part, I'm going to talk a little about mechanical characterization of carbon nanotubes that we use with using micropolar elasticity models. That is a non-classical model and also a molecular dynamics simulation. These works were done under the supervision of Professor Trovalucci with collaboration of Dr. Tuna and also with collaboration of Dr. Fantuzzi from Bologna University and Dr. Gavonlu from Shiraz University. As Dr. Tuna explained well, carbon nanotubes have many potential applications because they can be used in different areas of engineering like sensors, reinforcement elements. And if we want to use them efficiently, we need to provide deep insight into their mechanical properties. As we talked yesterday and also Dr. Tuna today, with atomistic simulation, we can provide a deep insight into nanoscopic phenomena. Because of the computational expenses, the length and time scales are really limited. So here, continuum models offer a solution for us. With continuum models, maybe it's better. With continuum models that are calibrated through atomistic simulation, we can preserve the accuracy of atomistic simulation while we use the efficiency of continuum modeling. And here you could see again some of our works that we have done using atomistic simulation, and then we proposed some continuum equivalence models for them. Here we use the shell theory, it was classical theory, and also here we use a modified form of Mori-Tanaka theory, it was also a classical theory, but we also simulated carbon nanotubes and we observed some size dependency and irregular behavior in carbon nanotubes that we were not able to capture with classical continuum theories. So we tried to use non-classical theories, and in this case we used micropolar theory to describe the observed behavior. Because, observations both in experiments and some atomistic modeling techniques show that there is a size dependency in carbon nanotubes. And we believe that this size dependency is related to the comparable length of the internal structure in carbon nanotube. We could also see my mouse. That is actually, we believe that is the carbon-carbon bond length in carbon nanotubes to its overall diameter. And because of this size dependency, the size effects are observed. Actually, in a lot of nanoscopic phenomena, we observe size effect because the overall diameter is comparable to the internal length. So we could not describe this size dependency with classical continuum theories, and we tried to use non-classical continuum theories or non-local continuum theories. Actually, usually non-local continuum theories are known as Erringen theory, but micropolar theory can also be considered as a non-local theory. Of course, in Erringen theory, as Dr. Tuna said, it's an explicit form because you could see what is the parameter that makes the equations non-local. But in micropolar theory, it is almost implicit because you cannot say that this is the parameter that is directly related to the internal length, but we have some other parameters that we can correlate them to the internal length of the structure. That I will explain a little more about it. Okay, what we did on carbon nanotubes were that we used molecular dynamics simulation, both in bending and torsional deformation, and we performed it on two sets of armchair and zigzag carbon nanotubes. And the diameters were ranging from 6 to 16 angstrom, and we fixed the aspect ratio to 5. This is what are the things that we did to minimize the computational expense, but then we showed that the results are independent of the aspect ratio. And you could see these are the two papers that we have published in the journals related to the bending and torsion approach. In the case of bending, we need to do some tricks, to make equivalent what we do in atomistic simulation and what we have in our continuum theories. For example, we did the bending deformation here, but we couldn't just, bend the CNC, just placing the two ends, but we have to resemble a bending that mimics pure bending, so we do not have any axial strain. We had to change them, and we had to make the two ends come closer to each other so that we do not have any unwanted axial strain. So that was the method that we proposed to avoid any unwanted axial strain. And then we obtained the curve, the moment versus angle curve for nanotubes, and using these curves and some formulation for the bending modulus, we obtained the bending modulus of carbon nanotubes. But here you could see that the bending modulus, this is the diameter and this is the bending modulus, and these are for the bending modulus for different diameters. And you could see that the bending modulus differs with diameter. But this cannot be described by local classical theory, because in local classical theory, we consider that we have a shell that is made of a material. It can have different diameters, but the bending modulus, it's something like the Young's modulus, but in bending, the flexural Young modulus. It shouldn't change with different diameter, but here we have the change. So we thought that we cannot describe this with classical theories. In this case, we used micropolar theory because we know that micropolar theory is used to describe a lot of materials with internal structure, including polycrystals, brick masonry walls, particulate composite, and also porous materials. So we applied it for carbon nanotubes. As you know, yes, these are the formulations. When, for example, in micropolar theory, we introduce another degree of freedom, which is microrotation. So we have another curvature, kinematic measure, which is curvature. And so in the equilibrium equation and in the constitutive equation, we have different material parameters. We have more material parameters. These material parameters here, like beta, gamma, alpha, they are indirectly related to the internal structure of the material. For this case, we also used another form of micropolar theory, which was constrained and also modified coupled stress theory that are a little simpler than micropolar theory. For example, in coupled stress theory, the stress and strains are symmetric, but we still have coupled stress, so we still have some other material parameters in our relations that can be related to the internal structure. Here you could see that we found the analytical relation for bending modulus in the framework of micropolar theory. It is the classical bending modulus that is multiplied by a factor named omega. That is the rigidity ratio. In the Cauchy case, it is equal to 1. But when we have micropolar theory, it is a parameter that, the size of the material and some other parameters are this one. It is equal to 1 when the material is, it is very high when the diameter is small, and then it goes slowly equal to 1 as the diameter increases. So if you see, we have the same shape here, and that's why we thought that micropolar theory can be a good candidate to describe this behavior. Well, we did an optimization approach, minimizing the data from micropolar theory and the data from molecular dynamics simulation. And here we saw that the micropolar theory can best capture the observed behavior. Although, we had also good results in coupled stress theory and also the constraint form, the approximate form of micropolar theory. And we had so much simpler, actually, equations in the latter two cases. And there was an interesting result here, is that we automatically find the length, the internal length of the structure, but the internal length was 1.4 angstrom. which is directly related to the bond length in carbon nanotube. So it actually shows the competency of our method, that the parameters that are found has physical meanings.
Sorry.
Yes.
Question. It seems that for large diameter, the negative scale is going to be vanished. The value do not converge. What value it will converge, because it's not converging.
Yes. Actually, you're completely right.
Razi, please, can you repeat the question? Because
Of course,
we
of
cannot listen.
One of the participants asked if how much is the value of the diameter, that it should tend, the curve should be flat and it should be equal. We should approach to the equal, for example, bending modulus. That doesn't change the diameter.
Okay, thanks.
Yes, the fact is that, yes, you're right. We have a plateau. It is going to be yes, it's going to be flat, but you're right that we need to do more simulations, even for very large diameters, to show that, yes, it is going to become flat. But the fact is that we have the relation for this, it is completely matched with the continuum relation. And when it is matched, we have the curve that goes to be flat in larger diameters. Of course, it can be shown that if we plots the whole curve here for the micropolar theory, we can understand that where is it going to become completely flat.
No, another question is that we believe that Cauchy model do not consider length.
Yes.
But my question is that why we're going to increase the diameter, the length scale parameter should be vanished somehow.
Yes.
But it do not converge to the Cauchy model.
Yes, you're right. This is when we use the Cauchy theory, because it cannot account for the length scale, it cannot be equal to this one, for example.
Yes, but even...
Yes. The fact is that when you increase the diameter, the question was that this is Cauchy theory, this is micropolar theory, and we say that in larger scales, when the diameter increases and the outer scale is not anymore comparable to the inner scale, it should become flat and it should approach to Cauchy theory. But why in this case it is not approaching? The fact is that, yes, it converges to Cauchy theory, but it approaches to the value that is going to be flat here. But for these values, we have calculated the Cauchy theory that it should not be equal to here, because it's actually an average of the bending modulus for these bonds. Okay. On the shear modulus. And again, we try to find some material parameters that can mimic this size dependency. Okay, I don't know if I need to go into details, but okay, we first try to solve the problem of torsion of a micropolar cylinder. So we use, of course, the polar coordinates. These are the displacement and microrotation fields. And here we introduce a function that is actually related to the geometry and also to the material. Then we use the polar relations for kinematic equations to find the stress and the strains and curvature. And then we substitute, this is actually the general framework when you want to develop the, you can start from the displacement, you find the strain and curvature, then you use equilibrium equation and the constitutive equation, and we find this equation for the for phi. And by solving this equation, we found this function with some with some constants in the in the function. How are these constants usually determined? No, we are not doing any experiments. We want to solve the equations in the continuum framework. Okay, so we have used that. For example, this is the micropolar material. It is under torsion, and we have the constitutive and equilibrium equations. When we are solving a problem, the boundary condition is also important. So this is a general form, and when you want to find these parameters, we apply the boundary conditions. So the boundary conditions were that we have okay, a torsion at this end, and we have a free surface on the outer wall of the cylinder. So with these, we found the parameters. So we found the shear modulus in case of micropolar theory and coupled stress theory. Again, we did the optimization approach, and we found the parameters here. As also professor noted, as you could see, the micropolar theory can best capture, the observed size dependency. We have also a good representation by coupled stress theory, but again, they differ a little from each other. And as professor said, in coupled stress theory, the stresses and strains are symmetric. But in micropolar theory, they are not. So here we conclude that there is an asymmetry in a stress and a strain that cannot be captured by coupled stress theory. And the material parameters we found from here were also in relation to the lattice structure of carbon nanotubes. Well, an interesting result was that the parameters that were obtained from the torsion were in consistency with the parameters that were obtained from the bending. That shows that the parameters are independent of the loading protocol. And again, we thought that it shows the competency of our method. Okay, thank you so much. And yeah, it is finished. Professor? Our professor is not here. I think maybe professor wants to add some complementary points. I just wanted to tell you that tomorrow it's apparently a strike on the transportation. So I don't think we can, change the schedule of the work, but if you would like to be present, as I recommend, I think you need to a little come earlier. But I think we start the course from 10, but you need to a little come earlier. And if you would like, you could bring your personal computer with yourself. Also, for the people that are online, when you're doing the simulations, you can also share your screen and you can ask your questions if you have any problem with your simulations. It's better if you could install the softwares that I have sent you before, but if not, we are going to, because they don't take so much time, so we are going to install it in the class.